The structure of the atom, section 4.4, unstable nuclei and radioactive decay. And the objectives of this lesson to explain the relationship between unstable nuclei and radioactive decay, characterize alpha, beta, and gamma radiation in terms of mass and charge. Some vocabulary to review is element, and some new vocabulary will be radioactivity, radiation, nuclear reaction, radioactive decay, alpha radiation, alpha particle, nuclear equation, beta radiation, beta particle, gamma ray. Although atoms might be rearranged, their chemical identity remains the same when in a chemical reaction. Another type of reaction, called a nuclear reaction, can change an element into a new element. In the late 1890s, scientists noticed that some substances spontaneously emitted radiation in a process that they called radioactivity. The rays and particles emitted by the radioactive material were called radiation. Scientists discovered that radioactive atoms undergo changes that can alter their identities. A reaction that involves a change in an atom's nucleus is called a nuclear reaction. The discovery of these nuclear reactions was a major breakthrough, as so no chemical reaction had ever resulted in the formation of new kinds of atoms. Radioactive atoms emit radiation because their nuclei are unstable, and unstable systems, whether they're atoms or people just doing handstands, gain stability by losing energy. Unstable nuclei lose energy by emitting radiation in a spontaneous process called radioactive decay. Unstable atoms undergo radioactive decay until they form a stable atom, often a different element. Just as a rock loses gravitational potential energy and reaches a stable state when falling to the ground, an atom can lose energy and reach stable state when emitting radiation. Right? We can kind of think of a radioactive atom as this person doing a handstand. To stand on your hands won't last very long. You're just naturally you're going to want to go ahead and find that sort of stability. To find that stability, your feet are going to come back to earth, and you're going to go ahead and take a new form. Scientists began researching radioactivity in the late 1800s. They investigated the effects of electrical fields on radiation. By directing radiation from a radioactive source between two electrically charged particles, scientists were able to identify three types of radiation based upon their electrical charge. And because putting these radioactive particles in between two electrically charged plates, right, one plate was positive, one plate was negative, right, they were able to go ahead and find three different types of radiation. The first type of radiation we call is alpha radiation. The radiation that was deflected towards the negative plate was named alpha radiation. It's made up of alpha particles, and an alpha particle contains two protons and two neutrons. Because it has no electrons to balance out those two protons, it thus has a +2 charge, which makes sense because they were deflecting towards the negative charged plate. Right? In this case, think opposites attract. An alpha particle is equivalent to that of a helium nucleus, and is represented as either in this isotopic notation, right, 4, 2, and then the chemical symbol helium, or just simply the Greek letter alpha. The alpha decay of radioactive radium-226 into radon-222 is shown below. So here's radium-226 that decays into an alpha particle, which means that radium-226 loses 2 protons and it loses 2 neutrons, and it becomes radon-222. All right, think about that for a second. If it loses 2 protons, right, if 88 were to lose 2 protons in the form of an alpha particle, right, 88 minus 2 is 86. If radium-226 were to lose 2 protons and 2 neutrons, right, losing a mass number of 4, 226 minus 4 equals 222. And if you were to go ahead and just substitute in this alpha particle for this isotopic notation of the helium nucleus, right, all the things would add up, right? 222 plus 4 equals 226, and 86 plus 2 equals 88. Right? Note that a new element, radon, is created as a result of the alpha decay of the unstable radium-226 nucleus. The type of equation shown above is called a nuclear equation. It shows the atomic number and the mass numbers of the particles involved. The mass number is conserved in nuclear equations. The second type of radiation is called beta radiation. This radiation was deflected towards the positive charged plate. This radiation consists of fast-moving beta particles. Each beta particle is an electron with a -1 charge. The negative charge of the beta particle explains why it is attracted to the positive plate. Beta particles are represented by the symbol beta, Greek letter beta, or just electron. The beta decay of a carbon-14 into nitrogen-14 is shown below. The beta decay of an unstable carbon-14 results in the creation of a new atom, nitrogen. Right? In this case, right, we have carbon-14, right, turning into, right, nitrogen-14 at the loss of 1 electron. Now, how does this happen? Right? Take a look at this. Here, the mass numbers stay the same, but it's the atomic number that changes. Right? If we kind of think about it, what occurs here is that you have a neutron, which is neutrally charged. That neutron collapses, and it turns into a proton, and it shoots off a beta particle. Right? When that neutron collapses and turns into a proton, the mass number doesn't change. However, the atomic number does. So here's an example of how the different types of radiation were discovered. Within a lead block was a radioactive source, and within this radioactive source, it was shot through a tiny, tiny pinhole. When that radioactive energy was shot through a tiny little hole and in between a positive and a negative plate, they noticed that the beta particles shifted towards the positive plate and that the alpha particles shifted towards the negative plate. And then what they also noticed was the third type of energy that was not even influenced at all by the magnetic field. But let's think for a second. Why is it that the beta particle had an influence much earlier than that of the alpha particle? If we think about it, remember that an beta particle is only 1 electron. One electron is very, very, very small compared to that of a proton or a neutron. An alpha particle contains 2 protons and 2 neutrons, which means that an alpha particle is very heavy compared to that of a beta particle. And therefore, the alpha particle was able to resist the change of its trajectory by the magnetic field much stronger than that of a beta particle. Right? And we can see that here we have a gamma ray, which was not influenced by the magnetic field. And we'll talk about that in just a moment. Right. The third type of radiation is gamma radiation, right, or gamma rays. A gamma ray is a high energy radiation that possesses no mass and is denoted by the symbol gamma. This is Greek letter gamma. Because they are neutral, gamma rays are not deflected by electrical or magnetic fields. They usually accompany alpha and beta radiation, and they account for most of the energy lost during a radioactive decay. For example, gamma rays accompany the alpha decay of uranium-238. Uranium-238 loses an alpha particle, meaning it loses 2 protons and 2 neutrons, and turns into thorium-234. But that energy that was within this alpha decay, right, is lost by gamma rays. Because gamma rays are massless, the emission of gamma rays by themselves cannot result in the formation of a new atom. The primary factor in determining an atom's stability is its ratio of neutrons to protons. Atoms that contain either too many or too few neutrons are unstable and lose energy through radioactive decay to form a stable nucleus. They emit alpha and beta particles, and these emissions affect the neutron to proton ratio of the newly created nucleus. Eventually, radioactive atoms undergo enough radioactive decay to form stable, non-reactive atoms. A section summary of 4.4. Chemical reactions involve changes in the electrons surrounding an atom, whereas nuclear reactions involve changes in the nucleus of an atom. There are 3 types of radiation: alpha, which has a +2, beta, which has a charge of -1, and gamma, which has no charge whatsoever. And the neutron to proton ratio of an atom's nucleus determines its stability.